Hi everyone, my name is Xuedou Xiao. I am a PhD student in Huazhong University of Science and Technology. Today, I'm going to talk about our research work on compressive offloading for age-assisted semantic video segmentation. Recent years have witnessed the pervasive use of semantic segmentation on mobile or IoT devices, ranging from smartphones, tablets, JAWS, autonomous vehicles to AR headsets. For example, Google Portrait Mode and YouTube Stories enrich their background settings. Virtual try-on and makeup apps become a reality. Self-driving cars and JAWS can obtain a pixel-level understanding of the surroundings. However, the wide application of semantic segmentation is attributed to the breakthrough of deep learning. Running DNN on mobile or IoT devices, however, remain challenging due to the limitation of computing resources, storage, latency requirement, and battery life. Driven by mobile edge computing, a promising solution is to offload the DNN inference tasks to the edge servers. However, with the explosion of vision-based applications and increasing scarcity of bandwidth resources, a compression scheme dedicated to semantic segmentation is urgently needed. I first introduced two mainstream approaches for DNN-based semantic segmentation. One is to input consecutive frames into DNN models, and the other is to perform semantic image segmentation on each frame or keyframes. The first approaches are generally computationally intensive. They are impractical for age-assisted video analytics such as ours, as they require to offload consecutive frames, leading to severe bandwidth consumption and large delay. We in this research adopted the second approach, that only keyframes are offloaded for semantic segmentation, and propagate across frames to obtain continuous semantic video segmentation. Then, for existing compression algorithms that use in semantic segmentation, most of them are based on uniform or fixed compression, such as JPEG, H.264, and GRACE, which respectively use the same quantization tables to the entire image or frame plane. In this case, the end devices must reduce the compression ratio of the entire image or frame plane to ensure DNN accuracy, which leads to a large additional bandwidth consumption. In contrast, the adaptive or non-uniform compression algorithms are always designed for object detection tasks that have clear region of interest. So, there is still a lack of dedicated compression algorithms for semantic segmentation tasks. Before proposing our algorithm, we conducted some preliminary experiments. By completely filling the exclamation box in the figure with the black color, which is equivalent to compressing this part with the maximum compression ratio, we can get the same ideal semantic segmentation result as in the original figure. Then, we can be sure that the spatial sensitivity of the image for semantic segmentation is non-uniform. In other words, the non-uniform compression can increase compression ratio without losing accuracy. Besides, we take another preliminary experiment to explore if regions around segment boundaries would be region of interest, and if we can get region of interest as easily as in object detection tasks. For this boundary-guided compression strategy, we allocate a lower compression ratio to regions around boundaries and higher compression ratios to other regions. The red areas in the bottom right image indicate regions with a lower compression ratio. Our experimental results, however, reveal that the boundary-guided compression strategy even leads to lower accuracy and compression ratio than the uniform compression strategy, such as JPEG. This indicates that the spatial sensitivity, or in other words, the region of interest of an image, is hard to predict in a handcrafted and heuristic manner. To accurately detect the region of interest, we propose STAC, which takes the first step to design a DNN-driven spatial-temporal adaptive compression scheme for semantic video segmentation, inspired by the work in Grace. The core idea is that the STAC utilizes DNN's gradients as non-uniform spatial sensitivity metrics of offloaded frames, and then generate and feedback spatial adaptive compensation steps for the image of frame plane in real time. We customize the compression strategy for the image or frame plane according to the maximum compression ratio that each pixel can withstand. However, this design entails some technical challenges. One is the large feedback burden and delay. First, the optimal compensation steps cover the entire image or frame plane, which are different for each pixel and need real-time offloading and feedback. So, the compression strategy is no less than the size of the offloaded image, which results in large additional bandwidth consumption. Second, the segmentation results are images or videos with full resolution. The time for the whole pipeline, including offloading, DNA inference, and feedback of segmentation results, can easily exceed the frame interval or latency requirements of various vision-based applications. Another challenge is that the customized compression strategy is not adaptive to changing video content. The spatial adaptive compression is customized to the offloaded frame, which may not adapt to subsequent frames with different spatial sensitivities. To tackle the large feedback burden, we propose a spatial adaptive scheme, which no longer targets the compression strategy designed for each pixel, but uses the divided regions as a basic unit for spatial adaptation. STAC takes a part of the online strategy generation process for offline by generating different levels of quantization tables with different compression ratios. These quantization tables incorporate the advantage of Grace by leveraging the DNN's sensitivity with respect to different frequency components of images. Then, STAC can select proper quantization tables for each region based on their DNN gradients and accuracy requirements. Therefore, only the levels of compression strategies selected by each region need to be fed back and offloaded. To adjust the program of the whole pipeline delay and the non-adaptability of customized compression strategies, we propose a temporal adaptive scheme that extracts pixel-wise optical flows to propagate both compression strategy and segmentation results across frames. Specifically, STAC catches and updates segmentation results and compression strategies of offloaded keyframe on the end devices. By propagating from the keyframe, both segmentation result and the compression strategy of the current frame can be obtained in real time. It is noteworthy that the only computational suggest at the end device is the computation of the optic flow and the propagation. To meet the real-time requirement, STAC adopts DIS, which is state-of-the-art in computational efficiency on CPU, and the running time are in the range of 10 to 600 Hz on 1024 by 436 resolution images on a single CPU core. This is fully compatible with devices such as mid-end smartphones, tablets, and AR headsets. Besides, DIS operates in a cost-to-5 fashion, giving STAC more flexibility to adjust computational costs. In our experiments, we adjust the parameters of DIS to reach the frame rates of different data sets. Furthermore, to determine whether the current frame should be offloaded as a keyframe to update the segmentation results and the compression strategy, we propose an adaptive floating mechanism. Specifically, we additionally use the dense optic flow to propagate pixels of the keyframe to the current frame. The key point is that The propagated frame and the propagated semantic segmentation have a 1-to-1 correspondence at each pixel. Then we compute the pixel level similarity, such as the PSNR, between the propagated frame and the actual frame to evaluate the degree of distortion. Once the PSNR falls below a predefined threshold, the semantic segmentation accuracy is not guaranteed and the adaptive offloading mechanism is triggered. The mechanism can autonomously adjust the offloading rate according to the real-time video content. We evaluate the STAC on 2 datasets, including cityscape and cam-width, and test 3 DNN models to evaluate the adaptability. We also compare STAC with 3 compression algorithms or codecs, including GRACE, H.264, and JPEG. GRACE is the state-of-the-art compression algorithm for age-assisted semantic segmentation, as both GRACE and JPEG offload each frame when processing video. We combine them with the propagation of semantic segmentation, which is the same as STAC for comparison. At last, we evaluate the STAC on a portable and small form factor Intel NUC. The specification of this hardware is comparable to what is available in today's mid-end smartphones, such as OnePlus 9 and Samsung Galaxy A52. Also, we deploy an edge server equipped with an NVIDIA Tesla T4 GPU. Experimental results show the better accuracy and compression ratio trade-off achieved by STAC compared to all 3 algorithms. Specifically, when the accuracy is the same, STAC can save up to 20.95% and 12.73% of bandwidth consumption on 2 DNN models respectively, and the reduction reached 24.23% and 33.53% compared to H.264 with constant rate factor equal to 13 and JPEG with Q value equal to 96. We also conduct extended experiments on adjustable parameters to explore their impacts and find the optimal settings. Theoretically, the more quantization table levels available, the higher the accuracy, but the heavier the communication load of compression strategy. Similarly, the smaller the size of regions divided, the higher the accuracy, but the larger the data size of compression strategy. Through a series of tests, we choose the number of available composition table levels to 16 and the size of regions to 3 by 3 blocks, which allows STAC to achieve relatively satisfactory accuracy while leading to a relatively small offloading bitrate. Also, we conduct experiments on another dataset, cam-width. It is shown that STAC outperforms other baseline algorithms in both accuracy and bandwidth consumption. Compared to GRACE, STAC can still reduce up to 11.63% of bandwidth consumption with comparable accuracy. In conclusion, STAC is the first to exploit DNN's gradients as a non-uniform spatial sensitivity matrix for spatial adaptive compression. It propagates both segmentation results and compression strategies across frames, and adopts adaptive loading algorithm to reduce the offloading bitrate and minimize the latency. Finally, we also presented that STAC can provide better accuracy and compression ratio trade-off compared to the state-of-the-art algorithm. That's all for today. Thank you for listening, and I'm happy to hear any questions.